Know how to control the generator, voltage and frequency, so let's go ahead. Firstly, let's see how the output voltage of the generator is controlled to get a fixed output voltage. Here, this is the actual voltage that comes out of the generator, and we need to check if it's on the allowable range or not. So we compare it with the reference value, that is the ideal value or the required value of voltage. Then we see the difference between the reference value and the actual value. So if the actual value is greater than the reference value, at this condition we need to decrease the actual value to be equal to the reference value. And for this we give the regulator a signal that is corresponding to the difference between the reference value and the actual value of the voltage to decrease the actual value for its magnitude to reach the reference value. And this regulator here is called AVR, or automatic voltage regulator. So it's a controller that has the job of adapting the actual voltage to reach the reference voltage. But how can the automatic voltage regulator do that job? So once the AVR receives the signal that the output voltage must be decreased, it gives the exciter a signal to decrease the excitation field current. So once the excitation field current decreases, the output voltage of the generator will decrease. This is because the generator output voltage depends mainly on the excitation field. Now suppose the inverse, which is that the actual voltage of the generator is less than the reference voltage. So with this condition, the difference between the reference voltage and the actual voltage will be given to the AVR as an input, and the AVR will sense that the actual voltage is less than the reference voltage, and the AVR at this condition will get the exciter as signal to increase the excitation current. So this excitation field of the generator will increase, and then the output voltage of the generator will increase because, as we mentioned, it depends on the excitation current of the exciter. So this closed loop control system is used to control the generator output voltage. Now let's see how the generator speed is controlled. Here is a full controlling diagram. And firstly, you must know that the frequency control is mainly a speed control. So when we control the generator speed, we are controlling the frequency or its frequency directly. This is because those generators that are used in the generation station are of the synchronous type. And at this type, the speed omega equals to 120 times the frequency over the generator number of poles. So you can see that the speed is directly proportional to the frequency. And if we manage to control the speed, we are controlling the frequency directly. So for measuring the speed omega, we sense it from the low pressure turbine shaft, as it's the same shaft of the generator. So by measuring its speed, we are measuring the generator speed. So we take its signal and compare it with the reference signal omega, that is the desired speed that we need the generator to rotate with it. Then we take the difference between those speeds, which is called the error, to be the input of the controller. Now suppose that the actual speed is larger than the reference speed, so the controller will receive a positive error, for example, which means that the current speed is larger than the reference speed, and we need now to decrease it. So the controller at this condition will give the actuators and the relays a signal to reduce the vent of the steam valve. So by closing the steam valve a little bit, we are reducing the steam that is input to the turbine. So when the turbine steam decreases, the speed of the turbine will decrease, and hence its shaft speed will decrease. So the generator speed will decrease as a whole. And by this way, we can decrease the generator speed than the generator frequency. Now suppose the inverse, at which we have the reference speed is larger than the actual speed of the shaft, which means that the generator speed must be increased. So the controller at this condition will receive a negative error, which means that a smaller actual speed than the required. So it will give the steam valve a signal to open the valve a little bit to increase the ingoing steam, then increasing the turbine speed, which will increase the generator shaft speed until the generator reaches the required speed. So by this way we can achieve the required generator frequency and speed. But since we are on the Riemann unit, which has some considerations of the voltage and frequency, so the speed control is very sensitive operation that must be controlled moment by moment. So let's see how the power network can affect the generator performance. Here suppose that we have those 3 power stations that feeds those loads through the infinite bus bar, and suppose now the system is stable with no problem. Now suppose that another load is added in the distribution zone that needs to be fed from the power system, and we know that adding a new load means increasing the current absorbed by the loads, but when the current increases, the torque required will increase because the torque is directly proportional to the current, but also we know that the torque is inversely proportional with the speed. So when the torque increases, the speed will decrease. And this means that the generator speed will decrease if there is an additional load that are added to the system. So this means also when the speed decreases, the frequency will decrease. Therefore, at conclusion, the overloading condition will cause the generator's frequencies to decrease. But this is an undesired case because, as we mentioned before, we need the generator speed and frequency to stay constant. And for this big problem, we have some solutions. The first one is to use the speed control by increasing the generator input steam to increase the output power of the stations. Then we can supply the new load with the required power. But this solution may not be available because in some cases the load added may be larger than the generation station full capacity. So at this condition we have the second solution, which is that to enter another generation station in the system quickly to cope with the increasing power, and this must be done quickly by some controlling steps. And now the last solution, if the first 2 solutions are not available, is to apply an operation which is called the load shedding, which is to disconnect the electricity from some loads that are not important until the overloading condition ends. Now suppose we have the inverse of this case, which is that a load has got out of the network. So this means that the current absorbed by the load will decrease, which means also that the torque will decrease, and hence increasing the speed of the generator, and then increasing the generator frequency. But this is a very dangerous case because the generator shaft has a limited range of its speed to increase until it. And if the speed of the shaft increased larger than this range, there may be a mechanical damage to the generator shaft, or we may not be able to control the generator. So we must decrease the generator speed and frequency immediately if its speed has increased. And this is done by decreasing the input steam of the generator turbine, as we mentioned before. So at conclusion, we wanted to say that the generator speed must be controlled carefully and it must be observed moment by moment to observe the system stability. So that's about the power system generators and its control. Hope that's clear right now. Thank you for watching and see you next tutorials.